Okay, on this example number 3, what we have is a uniform slender rod that has a mass of 15 kg, and on this particular problem, we want to determine the horizontal and vertical component of the reaction at point O and the angular acceleration of the rod just after the cord is cut. Okay, just after the cord is cut. So initially, we can say that it is uh, start from rest. Okay, start from rest. So okay, to begin with, we need to calculate the um, mass moment of inertia of this slender rod. By definition, there is the formula that we can get from the back of the textbook. Okay, for a slender rod, then just plug in the uh, mass, which is 15 kg, and then the total length, okay, of this particular rod, which is 0.9 meter, okay, zero point 0.6 plus 0.3, so it is 0.9 meter. Then you will get this mass moment of inertia of this particular uh, slender rod. Then we calculate the normal acceleration of this rod, which is of course it is initially at rest, so it is equal to 0. Then the tangential component of it is alpha um, times 0.15 meter. Where do we get this value? Okay, alpha, that is the R actually. Okay, so that particular value is okay. We know that the total length is 0.9, and the mid section of it is the middle is actually point, here is 0.45, here is 0.45, and if you can draw here, you can see that this portion here is, this one is, sorry, this one is 0.45, and on this part also 0.45, and therefore 0.45 minus 0.3, you will get 0.15. Okay, 0.15. Okay, on from this center of mass. Okay, center of mass should be somewhere here, and the point O here. So that's why it is a 0.15 meter. Okay, then using the parallel axis theorem, again, you can determine the mass moment of inertia of the uh, rod, sorry, a slender rod relative to this point O, because point O is our axis of rotation. Okay, it is there. Then uh, we already calculated the mass moment of inertia of this slender rod, and then just plus with the this mass time d square, dog. O is here, g should be somewhere here. Okay, and then this is uh, the answer that we get. Now we calculate the moment at point O here, okay, and we assume that counterclockwise is our positive direction, and then we look here, what we have is this is the let me remove this part here first. Okay, let me get rid of this because of okay. So at point G, we should have our weight, okay, at this point. And this particular weight is equal to mg. Okay. Then here we can, sorry, here, this is our m, 15. G is 9.81 because this is our center of our rotation axis. The weight is going this direction. It will create a counterclockwise motion. So therefore it is a positive. And then multiply by the moment arm or the perpendicular distance between point G and point O, which is here, okay, 0.15, okay, this one. And then that is equal to IO that we already calculate up here, multiplied by the angular acceleration. And then from here, we can easily determine the angular acceleration of the rod just after the cord is cut. Okay, that is answer for that. Then moving on, we look into the summation of the tangential forces, and on this vertical, sorry, on this particular direction, okay, vertical component, we assume that going down is our positive direction. And then you can see that the reaction at point O, the tangential reaction at point O should be going up. Okay, the reaction force OT is going up. Okay, because to support the weight of this rod. Okay, so that's why the direction is going up. And by definition, that by according to our reference axis system, we assume that going down is our positive, and this is going up, so that's why it is a negative. Okay, and then plus with the W. Okay, on the vertical component, we have W here, and also the the tangential reaction force at point O. Okay, then that all of that part is equal to m times this one is 16.35. It is the alpha here that we already calculated. It is one, okay, and 0.15 is distance between G and O, okay, and then after we calculate that part, we can get uh, the tangential reaction force at point O, which is 110 Newton. Okay, last part, we want to calculate or check whether we have any normal reaction forces in the pin. Okay, here we solve this the summation of normal forces. Going to the right is our positive direction, and since if we look carefully here, there is no other sorry, the reaction forces at point O. Okay, we can simply say that this is our O n. Okay, going that direction. That is equal to m times the normal angular, sorry, the normal acceleration of this rod, which is we already obtained it here. Okay, because it start from rest, so things this part will become zero, then this is also become zero because m is multiplied by um, zero. Okay, that's all. Thank you.